Welcome back to The Explainer. Today, we're opening up the ultimate lab manual to master one of the most powerful, everyday diagnostic techniques in a chemist's entire arsenal. I am incredibly excited to guide you through a complete masterclass on thin layer chromatography, or as you'll usually hear it called, TLC. Whether you're a seasoned synthetic chemist or you're literally just starting out at the bench, we're going to unpack exactly how this fascinating tool works, from the core theory all the way down to some seriously advanced lab hacks. Okay, let's dive right into this. Have you ever wondered how a chemist looks at a flask full of, well, dark, bubbling mystery goo and knows exactly what chemical compounds are swimming around inside? Without immediately relying on massive million-dollar machines, they turn to thin layer chromatography. TLC is that quick, cheap, absolutely essential technique that solves the mystery of unknown mixtures, and it actually allows us to monitor chemical reactions as they're happening in real time. Here's our roadmap for today's explainer. What is thin layer chromatography? The science of separation, step-by-step lab procedure, calculating retention factor, visualizing the invisible, and finally, troubleshooting and lab hacks. So, Section 1, what is thin layer chromatography? Let's get into the basics of TLC. It really helps to ground this whole concept historically by just looking at the word itself. Chromatography actually comes from the Greek words chroma, meaning color, and graphene, meaning to write. So literally, color writing. And that makes total sense, right? Because early experiments in chromatography were used to separate these vibrant, visible pigments in plant extracts, like green chlorophyll. By drawing a plant extract up a surface, scientists could physically watch the different colored compounds separate into distinct bands. Moving on to Section 2, the science of separation. Think of this as the ultimate tug-of-war of polarity. Now, what's really interesting here is understanding the invisible forces acting on our molecules. The whole mechanics of the separation basically come down to a chemical tug-of-war between two competing phases. First up, we've got the stationary phase. In TLC, this is usually an aluminum or glass plate coated with this incredibly thin layer of silica gel. Now, silica gel is slightly acidic, and it's packed with these silicon-oxygen-hydrogen bonds that act just like molecular Velcro. They grip incredibly tightly onto polar compounds. On the other side of this tug-of-war, we have the mobile phase. That's the organic solvent system you choose. The solvent travels up that silica plate via capillary action, and it tries to drag your chemical mixture right along with it. So your polar compounds get held back by that sticky silica, while the less polar ones, they just get swept right up toward the top by the moving solvent. All right, Section 3, step-by-step lab procedure. Let's head straight to the bench. Imagine you're standing right there at the bench, forceps in hand. The actual chronological process is beautifully simple. Step 1, you dissolve a tiny amount of your mystery mixture into a volatile solvent. Think acetone or dichloromethane. Step 2, you grab a tiny glass capillary tube and carefully dot or spot that liquid onto a pencil line drawn near the bottom of your TLC plate. Step 3, you place the plate into a closed chamber containing your mobile phase solvent to elute and just let capillary action do its magic. And finally, Step 4, once the solvent nears the top, you pull the plate out, let it dry, and visualize those separated spots. But here is an absolutely critical warning for Step 3. You literally must keep the solvent pool at the bottom of your chamber, below that pencil line where you spotted your samples. If your solvent level is too high, no way around it, your precious chemical samples will just completely dissolve outward into the pool of liquid at the bottom, instead of traveling vertically up the silica. You'll be left with a completely blank plate and a totally ruined experiment. And this brilliantly illustrates the resourcefulness of lab chemists. You honestly don't always need fancy equipment. A clean glass jam jar makes a perfect, incredibly inexpensive elution chamber. To get the absolute best separation, just line the inside of that jar with a piece of filter paper. It acts like a wick to saturate the air inside with solvent vapors, which prevents the solvent from evaporating off the face of your plate as it climbs. Oh, and always draw your baseline with a graphite pencil. If you use a pen, the ink is going to dissolve and elute right along with your chemicals. Congratulations, you've just chromatographed a Bic pen instead of your actual sample. Finally, when spotting, use a really light, quick up and down tap. Press too hard, and you'll gouge right through that delicate silica layer and completely disrupt the flow. Section 4, calculating retention factor. Let's look at the math behind the movement. So once your solvent has traveled near the top of the plate, you pull it out and immediately mark that final solvent line with your pencil. That brings us to the retention factor, or RF value. You calculate this by measuring the distance a specific chemical spot moved from the baseline and then dividing it by the total distance the solvent front moved. This gives you a simple decimal ratio somewhere between 0 and 1. And this RF value is absolutely crucial. It acts as the unique polarity fingerprint for that specific compound in that specific solvent system. It's exactly how chemists consistently communicate the results and identify known molecules. Now, there is a magic number in TLC, and it's roughly zero point 0.4. If you're using TLC as the sort of test run before scaling up to a massive preparative flash column chromatography purification, you're going to want to tweak your solvent mixture until the specific product you want to isolate hits an RF value of right around 0 point 0.4. That is the absolute sweet spot to make sure your target compound separates cleanly from any impurities on a much larger scale. Section 5. Visualizing the invisible. How do we actually see these colorless chemical compounds? So, the crucial point here is that most synthesized organic molecules don't look like vibrant green plant pigments. They are, for all intents and purposes, completely invisible. Here's a quick breakdown of the most common visualization methods we use to actually see our separated spots. The fastest way by far is to just slide your plate under a UV light lamp. The silica gel is actually treated to glow green under UV, while your chemical spots absorb that UV and show up as dark shadows. It works beautifully for molecules with conjugated double bonds or aromatic rings. But for compounds that just don't absorb UV light, we turn to chemical stains. You literally dip the entire plate into a solution and hit it with some heat. Phosphomolybidic acid, or PMA, is this amazing general-purpose stain. It turns almost any organic compound into a really distinct blue-green shade against a yellow background. Another great option is acidic vanillin. It actually turns different functional groups into these vibrant, totally different colors, which is a massive help when you're trying to differentiate two molecules that travel to the exact same height on your plate. Finally, Section 6. Troubleshooting and lab hacks. Let's fix those common TLC disasters. Let's be real, science rarely goes perfectly on the very first try. So let's rapid fire through some common pain points and how to instantly fix them. Streaky or massive blobby spots? Yeah, your sample is overloaded. It's just way too concentrated, so simply dilute it and try again. What if your compounds are completely stuck at the pencil baseline and just refuse to move? Your solvent is too weak. You need to mix in a more polar solvent like ethyl acetate or methanol. On the flip side, if everything flew straight up to the top solvent front, your solvent is way too strong. You gotta switch to something less polar, like hexane. And if your solvent line is slanted or completely uneven, your chamber probably got bumped or just isn't sitting perfectly level on the bench. Now, here is a brilliant pro tip for when things get really stubborn. Sometimes basic compounds like amines will stick incredibly hard to that acidic silica gel, creating these nasty, smeared streaks. You can actually fix this by adding just 2 to 5% of triethylamine to your solvent pool. That little additive binds to and deactivates the sticky silicon-oxygen-hydrogen bonds on the plate, letting your basic molecules elute nice and smoothly. And you know what? You can use a few drops of acetic acid to do the exact same trick for stubbornly sticky acidic compounds. To close out our lab hacks, I've got a few advanced tricks straight from the benches of seasoned synthetic chemists. First off, you can make your own custom ultrafine capillary spotters. Just heat the middle of a glass Pasteur pipette in a burner flame until it's soft, and then rapidly pull it apart at arm's length. It works like a charm. Second, if you ever suspect your compound is actually decomposing right there on the silica gel, run it 2D TLC. You spot your sample in the bottom corner, run it normally, let it dry, and then physically rotate the plate 90 degrees and run it a second time. If the compound is stable, it'll end up perfectly on a diagonal line. If it falls below that diagonal, well, it's falling apart. Lastly, if you're running a bunch of plates at once, pour a small bed of sea sand into the bottom of a really large chamber. It acts as the perfect base to hold several plates upright without them slipping and sliding into each other. It's honestly amazing, isn't it, that a simple glass jar, a tiny splash of solvent, and a thin sheet of silica can be used to decode the wildly complex chemical world right in front of us. Thin layer chromatography literally transforms the invisible into the visible, letting us read the secret identities of molecules. So knowing just how accessible and powerful this separation science truly is, what invisible mixtures in your own life would you want to decode next? Something to think about. Thanks so much for joining me on the Explainer to Master TLC, and I'll catch you on the next Deep Dive.